here. So this part, the cells here, and of course it's not one cell, there are many cells, will control the muscles that control the toes, and this is the hand and the lips and what have you. Two interesting anecdotes, not critical, but just interesting anecdotes. Look at the order. Can you see something interesting? It's sort of flipped, right? Not exactly, but the higher you go, the top of the cortex is controlling the bottom of your body. And as you go down, you go from toes to arms to head. It's not exactly because you see the lips and the eyes, but in general, you go cortex, you go top to bottom, but the body parts that are regulated are bottom to top. Not that it has any significance, but just to know. Is there anything else that is kind of awkward here? I don't know if awkward is the right word, but something that jumps up as what's going on here.
Well, the space devoted to your face is the same size as like the rest of the body.
Exactly. There is no proportion, right, between the actual size of a body part and the size of the cortex that regulates that body part. And the body parts here are shown as if they were represented by the neurons. You have huge lips, right? Look at the thumb versus the arm, okay? That is so thin. This is not what happens in reality, right? And this guy right here, you might think it looks like this guy. It's not, okay? Who's this guy? This is us, guys. This is what we call the homunculus, the motor homunculus. This is how we would have looked if our body parts would have been proportional to the size of the cortex that regulates them. Look at the arm, look at the thumbs. Why is that? And don't tell me we don't want to look like that. We like to look at like what we're used to, but why is that, basically? Why do we see such a small arm and such a huge thumb? Yes?
We need a lot more precise control over your fingers.
Wonderful. My arm, right? I'm not just contracting my arm like this. I need to have different movements. So I do need some muscles and I do need some neurons that will regulate these. But put your hands up for a second. Type virtually. Type on your computer, although not the computer, right? Think about how many muscles and how much coordination I need. So I need many more neurons so I can regulate and put that delicate, gentle, complex regulation of all these muscles. So I don't need a lot of body size in my fingers. I need a lot of control, much more than my arm. Questions about sonotopy before I start asking questions? Isabel. With that diagram changes, people use to some extent with regards to synaptic plasticity, but in very small manner. The question, sorry, I did not repeat it, was would that motor homunculus will change as we are using, maybe we are typing more, maybe we're doing some exercise so we have a greater arm, etc. So yes, but very mildly. Because we do have synaptic plasticity, we don't increase the number of neurons, but we will dedicate sometimes, we'll talk about it, some other parts to a given body if needed. Okay, let's continue. I did not ask you many questions today. I'm about to ask you, don't worry about that. Okay, we have the primary motor cortex. We go more anteriorly. What we'll find is the next part that we call the premotor cortex. It's also known as the motor association area. I typically do not use this term, but just because you might see that one, they're interchangeable. Let's do it again. Show me your hands. Let's type. Okay, now try to remember the very first time you learned how to type. Type now. What did you do? Like this? You guys were experts. Maybe like this, right? Right? My mom still does this. I'm kind of the middle between my mom and you guys, right? It will take me much more time, but still I can do that. So do we use, I mean, if I do this and I do this, do I use different muscles? No. So it means I don't use different neurons necessarily. But I have a better plan. I can coordinate those muscles much better. And for that, we have the premotor cortex. This is where we create a plan. The premotor cortex controls learned, repetitive, or patterned motor skills. Riding the bike, playing the piano, typing on a computer. Coordinates simultaneous and sequential actions involving the planning of movement. These are neurons, a lot of neurons. It's a much, much greater area physically, with many, many synapses, many short neurons that we call interneurons. And this is exactly the places where we build a plan. When we built a plan, when we learned how to type, we fired from neuron A to B, C, and D, and from D to E and F, and from C, etc., etc. But it didn't work so well. So we had a negative outcome. So we generated an IPSP in that path, and then we added another one until we found the best place. And that's the path we're using. We'll talk a bit about memory next week, but in general, when we talk about memory, there's no region responsible for memory. There's some regions in the brain that have some function, but basically, memory is everywhere. Memories are networks, are paths, synapses that continue to function. So when you learn how to type, you, in a way, fixed the best paths that will allow to coordinate all those muscles. Now, which neurons, where can I find the neurons that eventually will say, okay, contract so I can type, and you contract and you contract and you contract. Where can I find them? The ones that actually tell the muscles to contract. Where are they? We talked about that not long ago. 1, 2, 3. Primary motor cortex, exactly. So the premotor cortex neurons are not the executors. They will synapse with the right primary motor cortex neurons, fire. As a result, the primary motor neurons, the right ones, will fire at the right time, at the right place. And that indirectly, eventually, will lead to contraction of the muscles and coordination of the movements. Okay? Any questions about premotor versus primary motor cortex? Yes?
Is the premotor cortex kind of like what's responsible for like muscle memory?
Is the premotor cortex responsible for muscle memory? In a way, yes. We'll talk a bit more about muscles, but I can say yes, to some extent. From my past experience, I expect more than one question. It cannot be so clear. Yes?
So when people start losing their memory and they don't remember like present things they remember.
Can you wait for that question? Just a bit? Great question. Okay. Learning catalytics. It's about time. Answer this one. Why can Jim still type? He could still type. Show me your hands, you're Jim after the accident. How Jim types. Like we started, like Jim learned how to type, right? What he lost is the ability to generate a plan. And here's answering your question, what happens if we memory or accident or anything like that. Now, the question is, can Jim learn again how to type in a more, with a better plan, basically? The answer, it depends. It depends on the degree of damage. But because of synaptic plasticity, if this area is not completely damaged, he can teach it himself. Maybe he will not reach the perfect performance because he doesn't have all those neurons and all those synapses. But again, this is synaptic plasticity. He will be able to do that, at least to some extent, depending on the damage. We see that a lot with people who had stroke. And people who had stroke that cannot talk, for example, and need to reteach themselves how to speak, even the language itself. But because of synaptic plasticity, they are able to do that. How much? That depends on how much damage it was. So that's the difference between making a plan and execute a plan. Okay. This will probably not work with the audio stuff, but I still want to show it. Let's see if we can see something. If not, no worries. No, we cannot see it here, of course. Never mind. So, not critical. Oops, sorry. Give me a second. Speech involves many muscles that have to be extremely carefully coordinated to generate speech. Speech is pretty unique to humans. I'm not talking about making sounds or making communication. I'm talking about speech. Okay? So in a way, controlling the muscles of speech is the same idea as controlling typing, right? Coordinating, making the plan. But this requires so much regulation that during evolution, there's a whole part in our brain, in our cerebral cortex, that is dedicated to speech. Not only to speech, but we'll focus only on the speech. And that's Broca's area. So the concept is the same concept as the premotor cortex. We are we're coordinating, so we can execute a better speech. It's not found in both hemispheres. This is one of the cases when we find it in one hemisphere. In most cases, it's in the left hemisphere. In some cases, in the right. Nothing to do with whether you're left-handed or right-handed. But it will always be in one case. Yes, ma'am.
So if this part is the lip, would you still be able to speak because you're speaking on?
So Yonda is asking the right question. What happens if this is messed up? We will leave that, and we will address this on Tuesday. Okay, we'll show you some example of what happens when this is compromised. Okay, but this is exactly the way to think about it. So Broca's area is found typically in the left hemisphere. It creates a plan for speaking. Will we, with the disclaimer of everything simplified and one big lie, but based on that, will we see neurons, axons, coming out of Broca's areas to the skeletal muscles governing speech? Or where else? To the primary motor cortex, exactly. Just like the premotor cortex will send signals fired towards the primary motor cortex, so will the Broca's area. Do we see axons that go to the premotor cortex? To some extent, yes, sure, but the main thing here is going to go, the main activity is going to go through the primary motor cortex. Any questions about speech, Broca's area, motor areas? These are the three motor areas that we're going to discuss. Any questions? Yes?
How is it possible that usually it's in one hemisphere, but could be like in another between humans? Wouldn't that lead to...
So if it's in another hemisphere, this is next week when we will talk not about contralaterality, but about the relationship between the left and the right hemisphere. We will see how we can compensate. Okay? There's a communication going on between the left and the right. And as we will see, if the Broca's is on the right, there will be other things that are typically on the left that we will find on the right to compensate. These people are functioning perfectly. If you have a damaged Broca's area, that's a different story. Okay? But whether it's left, it just happens to be left. Even if it's in right, they will be fine. We just need to change the wiring. Okay. Okay, let's talk a bit about the parietal lobe. That's the geographical part, right? The anatomical part. Here's the central sulcus, and we're talking about the postcentral gyrus. Again, I'm not going to ask you about the anatomical part. This is just to orient you. We're going to talk about the physiological regions that are responsible for our physiology, for our function. And the first one is the primary somatosensory cortex. Okay? It's primary because it's primary, it's cortex because it's cortex, and it's somatosensory, which is responsible for, first of all, for motor orthosensory. Okay, Captain Obvious, that's pretty easy. What does it mean when it says somatosensory? What does the soma mean? Coming from the soma, from the cell body. Remember when we learned in the beginning about the different parts, we have visceral, we have somato. This comes from the soma. I'm touching the desk right here, right? No, I'm using the same example I used earlier on. I'm touching with my left finger the podium. Sensory signal will go, is that afferent or efferent? Afferent with an A. Will go synapses with my spinal cord. There will be a neuron going up, a synapse in the thalamus. We'll talk about that next week. And then at some point, it's going to make it, we said, to the right, to this right, the primary somatosensory cortex. So we get inputs from sensory receptors that are found in our periphery, in the soma. This includes the skin more than anything else. We have lots of types and lots of molecules of sensory receptors in our skin. We also have receptors in our joints. We'll talk about them next Thursday when we talk about sensation. But in general, we talk about something we call proprioceptors. They're found in our joints and in our skeletal muscles and give us a sense about stretching, mainly stretching. And all of these will go to the primary somatosensory cortex. Okay? Just like the case of the primary motor cortex, here as well, we have different regions responsible to get signals, sensory inputs from different parts of our body. And just like that, we can have a map. How do we call this map? How do we call this map? Somatotopy. Okay? And we actually have the same, not exactly the same, but a similar ugly person that is like, we need to start to understand. This is us. This is how we look like, guys. Sorry for that. Okay? Not very different from the motor, but with some differences. Look at the pulp. Look at the palm. Look at the thumbs. Look at the lips. They're so important for sensing sensory inputs. And again, the same idea, top to bottom, bottom to top, and no proportion between the body parts and the actual parts that regulate them, as we discussed. The same idea. Just small differences. Okay? The second part, as we go more posteriorly, we find the somatosensory association area. I typically, some of you know me already, I'm not a person of small details. I don't care if you say the exact right word as long as you understand the concept. I will say that because these names look so much similar, I will be strict in this case. And when I ask you a question in the exam about which happens where, if you write to me somatosensory cortex, and about the association area, that's completely wrong. Okay, so just make sure you know exactly those areas. We don't have too many of those. Okay, put your hands in your pocket for a second, and I'm looking for if you have keys in your pocket or a cell phone in your pocket. If not, if you don't have anything in the pockets and you have something close by, backpack or something like that, not too much of a mess, try to find your keys without looking at them. Without looking. Okay, if you cannot reach it, don't worry about it. We have enough students to do this experiment. I'll use mine. I have my keys here. What I want you to do without looking is to try to identify a specific key, your home key, for example. Or if you have a cell phone, a smartphone, maybe try to find a specific key on the smartphone. Maybe the send or on or whatever. Something you think you know, but don't use your eyes. I'm going to use my phone house key. Okay? Now take it out. Check to see if you're right. I was. How many of you were right in the guesses? How many of you were wrong? How many of you are honest? Andrew, 1. Good for you. Okay. So now let's think about what happens. Let's think what happens in our brain. Okay? We'll follow my example. I touch this key. When I touch the key, a signal came from my right finger, from my right hand, all the way to the spinal cord, then to the thalamus, and then to which part of my brain? Which part of my brain the signal went to? 1, 2, 3. Somatosensory cortex. If I stop here, what does my CNS, what does my brain, what do I know about the event that just happened? What information did I get? What happened at this point? Let's say we are cutting anything after that. Just this part. Diego. I touched something, exactly. I just got information that I touched something. That's it. The signals from here, and of course it's not just one receptor, there will be different receptors, different neurons, and they will come to different types of different cells on the primary somatosensory cortex. It's not just one. Okay? So this is responsible for conscious awareness. We are aware of this. Not, as we will talk when we'll talk about sensation, not all our sensory inputs we are aware of them. Actually, most of them we are not aware. You are not aware or conscious about the pH level in your blood. You're not aware or conscious about the blood pressure. It doesn't reach the cortex. This is why you're not aware. This is what you sense when you get a conscious understanding, but you just touched. From here, the signals will go to the somatosensory association area. And then what we will see in that area, we will compare the inputs to information that we already have. And again, information is burned into our cortex through different synapses and networks. And then when I touch the key, it was only touched so far. But now I can say, okay, this is metal. This is not plastic. I know, my brain knows the difference between touching, the texture. This has a shape. It's round, it's long, and this means it's probably a key. It's not a cell phone, right? Because it's a different shape, even without looking at that. I know that my home key is a bit smaller, a bit shorter, a different shape than my other keys. So I'm comparing all of this, and then I make a conscious decision about information of what I exactly touched. This is the difference from received to perceived, okay? I made analysis, processing, so I can get the best information, and for that I need the association area. Please look at the colors. It's so much bigger. It has so many more neurons, synapses, etc. So the somatosensory association area processes and analyzes the sensory inputs that come from the primary sensory cortex. I can still say touch if I just touched it and if my whole association area was compromised for whatever reason, because of an accident. But I would not be able to distinguish between a key to a smartphone, to a cat that I'm not holding in my pocket, but never mind, to whatever you can think of. So just to summarize this, the primary somatosensory receives information, and the somatosensory integrates, forms comprehensive understanding, determines size, texture, and the relationships of the parts. Questions? This concept of two different parts of a region, one cortex and then association area, is not just for the somatosensory. It also applies to other, not all, but other sensory regions. A good example would be the auditory areas. We have one auditory region, but it's separated into a primary auditory cortex and an auditory association area. Geology doesn't work, of course. Should have been a baby to do that. Does it, but I'll try to do the best I can. What am I doing in the first part? What am I doing in the second part? Ha ha ha. Huh. 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 What are you doing in the first part? What are you doing in the second part? Right. Okay. When you heard me, where did the sound go to? The sound went to your ear, and from there you have hearing receptors, and then there you have neurons, right, that will go all the way, thalamus again. Eventually they will reach which part? The primary auditory cortex first. At the cortex, we're able to hear the sound. You're able to say, I heard the sound. In this case, by the way, it's not just hear the sound, but you'll be able to tell the pitch, high, low, okay? Because it's not processed at the level of the cortex. It's different. We don't talk about the ear, the hearing, unfortunately, but it's about the hearing organ. So you can learn about sound, you can learn about volume, low amplitude, high amplitude, and you can learn about the rhythm. But you couldn't tell, if it was just the auditory cortex, you couldn't tell whether this is a dog or a person. You couldn't tell that this is Giddy and not Brian. You couldn't tell that I'm, what? Laughing and not crying. Okay? This all takes place in the association area. This is where we are putting together all this stuff, comparing it to what we know, right? Because if you don't know anything, maybe you'll think laughing, crying, the same thing, right? But if you know, you compare it to memories. This is where we process. Okay? So, no, it doesn't want to move. We'll just leave it. We'll continue on Tuesday.